cost of the solution. Okay, the other is search time, which is equal to number of expansions. Right, it's a kind of approximately connected to number of expansions. Cost of solution will always be optimal as long as the heuristic is admissible. Okay, now the search time cannot be worse than h equal to 0. If you start using any reasonable h, it can't be worse than h equal to 0. H equal to 0 is the blind search. Okay, yes.
Can you switch heuristics halfway through?
Can you switch heuristics halfway through? Yeah, as long as you're comparing apples to apples. When you switch, then you can't just say the node that came into the queue previously will still be using H1, while the new nodes will be using H2. If midway through you say, I'm sick of H1, now I'll start thinking of H2, use H2 for everybody. Then that's fine. I don't know there is an advantage, but you won't be wrong if H2 is also admissible. Okay, since I went through this funny picture, I want to show this to you now. Okay, and so let's play this game. Okay, that's H star for some random problem. First question: does this problem have a solution? What? Right.
No matter what, it's not infinite in this graph.
Infinite is fine. Okay, so that's your answer. That's good. Try it. I always appreciate people who actually try an answer. So anybody else who wants to say the other answer and give the answer reason? Yes.
I say no because it never reaches 0.
Exactly. Right? One thing you should realize about h is for the goal, the h should be 0. If the goal comes and bites you and you still don't think it's a goal, then you are on the wrong business. You see what I'm saying? One way you can be doing extremely bad search is you pick the goal node for expansion and throw it out and continue doing search. You see what I'm saying? And that would happen because you didn't realize that h equal to 0. Basically, you didn't know that it's a goal. And if you don't know it's a goal, then you won't realize that h equal to 0. In fact, the other very interesting point is, can you have an admissible heuristic which has h value not equal to 0 for the goal nodes? It's a very simple question, but it's quite deep, right? Somebody said no.
I said no because then it would be a lower bound.
Exactly. Because if you are at the goal node, how far do you have to travel to reach the goal node? 0. If your h is anything other than 0, then you are sunk. Right? Even just an arbitrary line I drew on a graph, and already I can make 2 interesting points. Okay, but now let's assume that there are actually goals. Maybe it sort of touches G here, 0 here. Okay. So actually it was a bug I made into a feature. When I drew this graph, I forgot to make it touch G, and so in fact it doesn't make any sense to talk about admissible heuristics in this case because there is no solution. So I made it into a feature by asking, does it have a solution? And now that we had the discussion, act as if somewhere on this x value axis it did touch 0. Okay. Now I want you to first of all realize the reason I drew this is these are the search nodes, this is the heuristic value, and a heuristic is a function. It's not a single value, it's a function. You have to understand that. So when you say a lower bound, you need a function that is always lower than this function. Okay, so keep that in mind. So I have this green guy, H1. Is H1 admissible? Okay, marginal the fact that each of these guys should have hit 0 somewhere, but ignore that for a minute. Is H1 admissible? Yes. Right? Okay. H5, is that admissible? H4, is that admissible? It's mostly admissible, but there is no such thing as mostly admissible. Right? If you cross H star even once, you are out. you are banished. Okay, H4 is not admissible. This is very important to understand. If you want to show that a heuristic is inadmissible, all you need to do is a single counter example. One node where the heuristic overestimates the cost. H2, is that admissible? H3. H3 is not admissible? It is admissible because it's still below the red. Oh, no, wait.
You cross the red one at the.
Oh, okay. You guys are smart. Very good. Extremely good. Okay, that's very nice. Yes, that's right. And it was supposed to be done. Then it will be admissible. But yes, I think sometimes you might assume that I'm more conniving than I actually tend to be. But okay, so mostly X3 is admissible, but if you do take this fact that it's crossing, yes, it's not admissible. Okay. This blue, again, ignore this part. Okay, imagine this part doesn't exist. So, is the blue admissible? It's very hard to draw these kinds of amazing curves with PowerPoint. Okay, is that admissible? What is it? It's max of H2 and H1.
It's like the most optimal.
It's not the most optimal yet because H star is the most optimal.
Right, but like from whatever option.
Yes, so if I have, so this actually tells you, as he was saying, that if you have two heuristics, before you had H3 and H2, if you ignore this part, neither H3 nor H2 is more informed than the other. Because in some cases H3 is bigger than H2, in some cases H2 is bigger than H3. Both of them look at H1 and say, what a loser. Right, because H1 is lower. It's admissible, it is lower. So H1 and H3 are more informed than, H3 and H2 are more informed than H1, but neither of these themselves are better than each other. If I have two heuristics that neither of which are more informed than other, but they are both admissible, I take maximum of that, I get a heuristic which is better than both. Right, because max by definition is going to be more informed than each of them. So this tells you sometimes, in fact, this was kind of related to that question somebody was asking about pattern databases. Sometimes if you wind up getting two very different heuristics for the same problem, both of which are admissible, taking max of them, you'll never go wrong. But what you really would like to do is taking sum of them. That unfortunately you can't. You see what I'm saying? If I have two heuristics, two bounds, if I add them up, it will be a bigger number than just take max. If I can do the add, it would make me feel very good because it will be a much bigger heuristic. But then it might cross over H star somewhere. Additive admissible heuristics are much harder to get. So you generally are not guaranteed that adding will give you admissibility, but taking max will always give you keep admissibility, and so you'll be more informed. Yes?
Are there any cases where you can use like parts of H4, for example, where you know for this amount that it would be like...
Yeah, so if you know where it is crossing, yes. But then in some sense, then you would be rebuilding a different function then, which is then realizing where it is crossing over. Okay? But that picture, by the way, it's very useful because people tend to think of heuristics as if they are point estimates. They're really functions. And when you told me that H2 is inadmissible because it crossed over here, you are all being extremely smart. Because you learned a lot more than most people realize when they read A star search first. That it's a global property. It's for all n, h of n is less than greater than. Okay? Okay, so we'll go from this and then go back to what we are discussing. One more thing I want to discuss here is, so I told you how you get heuristics for tile puzzle, right? I looked at the fact that for the tile puzzle, okay, you can assume the ability to move the tile directly to the place you want, in which case the distance would be equal to the number of misplaced tiles. That would be admissible. Or you can also assume the ability to move only one position at a time and take each, tile to the right place it's supposed to get to. That would be the Manhattan distance for that tile. And you add up the Manhattan distances, that will still be a lower bound on the true constant. And then I also told you about these pattern database heuristics, which are actually, I didn't discuss it at length, but they are essentially saying solve a part of the problem optimally, and then use that as a lower bound. So in a strange sense, when I was trying to find the optimal path to that guy earlier, I was thinking of uniform abstractions, right? I was thinking either all of you disappear, okay? But what if I kind of start saying, I only assume this part of the room disappears? That would still be an abstraction of the original problem. What if I assume that every odd numbered seat becomes like an empty seat? I can walk through it. That's also an abstraction. In all those cases, the distance estimates I get will be closer to the two distances. Not this one, but at least the even numbered ones will be different. And so those would actually be non-obvious heuristics. When people think of heuristics, they think of a two-line heuristic, but it can be any abstraction of the problem. Okay, one other thing that I wanted to mention is path planning. Okay, so this is actually this path planning. So this guy is the goal, this is Rao, and these are all the obstacles. I mean, they don't look like this right now, but there are various obstacles in the free space, and I'm trying to find, the robot is trying to find a path from where it is to the place that it wants to go. That's path planning. A-star search is used pretty much out of the box in every path planning problem. Okay, now the interesting question is, how do you get the heuristics? Okay, the simplest idea is assume that all the obstacles disappear. If they disappear, I should do it once in a while because I can later. If they disappear, then the shortest path is the straight line distance. That would be a lower bound. The other is for each obstacle which is of this irregular shape, I will inscribe each of these obstacles. This is a two-dimensional problem. I'll inscribe each obstacle with the biggest circle that I can put in there. Right? Then it actually turns out that that is a simple problem to solve. If all the obstacles are of circular shape, then actually one of the things you can do is you can shrink those circular obstacles to point size and make the space bigger. That's one idea. I won't go into the details. Otherwise, if you don't want to do that, you can still get all the tangents between the circles. Do you see what I'm saying? You consider all the tangents between the circles. And the optimal path has to pass on the tangents. Think about that. Optimal path for this green space has to pass over the tangents. And that path cost will still be lower bound on the true path cost. Okay. Now I could, instead of doing circular abstractions, I can do polygonal abstractions. I take for each obstacle a reasonable polygonal abstraction. Okay. In which case, once again, you will start talking about these ideas called Voronoi diagrams, which are essentially you're connecting the corners and you're traveling on those corner points. Okay, that is an abstraction too, but the cost in this abstract space is better than the cost in this abstract space, in the sense it's closer to the true cost. Okay, so you have least informed, next best informed, then H star. One question. Instead of circles inscribing, I could do circles. What's the other way? Other word. Inscribed circles, and what's the other circles? Circumscribed circles. What if I do circumscription? What if you circumscribe circles for each of the obstacles? Yeah?
Then you're making the problem harder, your abstractions.
Then what happens?
Then it has to go further.
So then what happens?
You cross each star.
Exactly. You see, again, so you basically, it looks, when we started discussing it, looked like, how the heck do I make H be less than H star? It looks like some kind of a black art. It's not a black art, it's just a question of abstraction. Okay? When you put when you made the obstacle smaller than it is, you abstracted it. When you made the obstacle bigger than it is, you didn't abstract it, you added more constraints. Now, solving the problem is actually easier, just as easier if not easier, if you make the obstacles bigger than they are. I have this new idea called 15-fold circumscribing. That means for each obstacle, I take the circumscribed circle, make it 15 times larger. It's a very efficient heuristic in most cases because it will show that goal can't be reached. So I say there is no path. Very fast to solve. What's the problem with it? It's not admissible. Okay, you say goal can't be solved and people are actually solving it. Okay, and so by adding constraints, you make the heuristic inadmissible. The moment you make the heuristic inadmissible, all the guarantees are done. As long as you only remove the constraints, you are abstracting the problem, and then you will be lower bound. Okay, something which was like a random abstract discussion about lower bounds becomes very concrete here in terms of what it is, what does it mean to add constraints versus remove constraints from a problem. Okay? Okay, so going back to the more abstract discussion of A star, and I want to just prove, I want to say that I have proved at least, that basically A star is optimal. And you can prove A star search is optimal. I already said that earlier. Essentially, the basic idea is n double dash is on the search queue at the same time n as on the search queue. And then you pick n and terminate it because it's a goal node. Your thinking here is there is a path through n double dash to another node n dash, which is another goal, and that path cost is cheaper than this true path cost. In which case that would be a cheaper goal. And you know that it's not possible. You know that it's not possible because when you picked n over n double dash, the n double dash you compared f of n and f of n double dash. F of n is g of n plus h of n. If n is a goal node, h of n is 0. That means f of n is g of n. F of n double dash is g of n double dash plus h of n double dash, which is the path from n double dash to the optimal goal, except h is a lower bound. So whatever is the true path is going to be costlier than that. So what I'm saying is, I already have a goal that's 9 units costly. I have this partial node here, which is 9 units costly. A partial node here, which is, let's say, 10 units costly. Okay? And I'm worried that it might become cheaper. It can't, because the 10 units is the estimate. It's an optimistic estimate of the distance. The true distance can be either 10 or more. So if you kill n double dash because it's more than n in terms of f value, you would not miss any optimal goal. Notice that that argument would break down if this estimate was an overbound and not an upper bound. It's an upper bound, not a lower bound. Because if I say, I think the path to n double dash is about 10 units, could be more, could be less. I don't like this could be more, could be less. Because if it could be less, and if this is 9 and this is 10, maybe the less could become 8.9. Then I won't be optimal anymore. You see what I'm saying? So it was very important that the estimate from n double dash to the goal is a lower bound. So that is, the estimate is optimistic estimate. Because it's optimistic estimate, the true cost can only be worse. And if you are picking n over n double dash right now, that means n double dash is at least as bad as n right now. So it can only become worse as you go on. So there's no way you can do that. That's the proof. Okay? Another way of looking at the optimality argument is, let's see, where is it? Another way of looking at the optimality argument is, is this. If you have, this is your old Romania graph, Okay, one interesting thing is what happens when you are doing breadth first, uniform cost search versus A star search. Uniform cost search essentially looks at frontiers that are circular around the starting node. They're looking at circles of different increasing sizes from the starting node and seeing if the goal node is on any of those circles. That's what uniform cost search is doing. And because these circles are, each of them is bigger than the other one, by the way you're constructing it, if you find a goal on this circle, that's because you haven't yet found a goal on this circle. That means it's the most optimal you can get. And these are all equidistant circles, obviously. I mean, circle basically means they're equidistant from the point. When you do A star search, the frontiers that you search would be nicely pointed towards the goal. Okay, previously, you didn't know where the goal is. You're just saying, if I'm trying to figure out where my home is, I'll consider everything 1 centimeter radius from me, 2 centimeters radius from me, 3 centimeters radius from me, etc. until I find my home. That's blind search. But if I have an idea as to cost to go from each of the nodes to the home, then I will start looking at frontiers, search frontiers, which are increasingly pointed towards the goal. In the best case, when you have H star, these things will become lines. So you just go directly towards the goal. So that's the analogy we have. Okay? Okay, I have 2 more things to do, and then we will be done with A star search. Actually, this one is fun, so let's do this. Here is an example graph. Okay, and I will put some heuristic values on the nodes, and you wake up and tell me whether the heuristic is admissible or not. This is again an abstract problem, so you should just basically check whether it's whether admissibility criterion is holding. Okay, that's the magenta. Is the heuristic admissible? So previously you already know these numbers. This is the edge cost, and then I also gave the heuristics for each of the nodes. So the question is the heuristic admissible? Anybody who would like to say it is yes, the heuristic is admissible?
Yeah.
Who? Yes?
Minimum distance. So those are all the least optimal options because they're way higher than what they actually are.
So you're saying the heuristic is admissible or not admissible? It is admissible. Okay, so the question is, if you take C, point C, the heuristic value for C is 28. Is that a lower bound on the true cost to go from C to the goal? So it's not admissible. Do you see what I'm saying? So it's admissible here because 7 is less than 9. Okay, it's admissible here because the 25.2 is less than 20. It's admissible here because 25 is less than or equal to 20. But it's not admissible here. 28 is not less than 25.1. And a heuristic is admissible if it is for all n, it's a lower bound. So actually this idea that the heuristic is admissible here is the wrong thing to say. I have to say it's a lower bound here, 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 it's not a lower bound here, so it's not admissible. It has to be lower bound everywhere for it to be admissible. Okay? How about this? Okay, let's see. Answer the only question. Yeah, magenta H is admissible. The green H, is the green H admissible? Okay? Anybody thinks green H is not? Yes, yes, sir.
I can see why it would be and it wouldn't be. I would say it's not because it's 0. We have 0 values for those things.
0 is, well, okay.
If you consider 0 as being admissible, then yeah.
H equal to 0 is considered okay. This is actually a good point, by the way. I think your points are well taken. I appreciate the fact that you're paying attention. Because G cannot be 0. I mean, the edge cost can't be 0. But H can be 0. In fact, uniform cost search is using H equal to 0 everywhere. Okay? And by the way, I think we learn by looking for inconsistencies in our understanding. So what he did is the way you learn. Okay? If you did not even think that possible inconsistency exists, that's because you were basically looking at your cell phone most of the time. Okay. So green H is admissible, right? Because every place it is lower bound. That's all. Lower admissible means it's lower bound everywhere. Okay? There's a question. Yes.
So can you shift to the purple zone?
I got it magenta. Why do you call it purple? What are you? Go ahead. Yeah.
So
I don't know. It's not
when-
magenta actually. It's purple. What was it?
From the A, it will directly reach to G if we start from A.
Yeah.
So we are reaching the solution.
So what happened?
So
There is a cost of reaching. This is the edge. The edge cost is 9. So you do have to distance. You have to travel distance 9. True distance is 9, and I'm assuming the estimated distance is 7. So it is still admissible. Just because there is a direct road from here to Los Angeles doesn't mean I'm already in Los Angeles. I still have to travel on the road. Okay? Okay, so the green. Now, I want you to think about the craziness of this heuristic. Okay, it's admissible. But one crazy thing about heuristics is they're supposed to be distances, but they might wind up not having semantics of distances. Okay, now what is a semantic of a distance? What makes something a distance measure? What?
Positive.
It is positive. Should be positive. What else? Yeah?
Should have the triangle inequality.
Wow! Like wow, right? I mean, where did that come from? Right? Distance measure should obey triangle law of inequality. How many of you know this? Well, of course, that guy knows. The rest of you should know. This is stuff that you're supposed to know. Good distance measures obey triangle law of inequality. Now, what is a triangle law of inequality? What's the triangle law of inequality? Sum of any two sides of the triangle should be equal or greater than the third side. That's the triangle law of inequality. This is the stuff that you were supposed to have done in the geometry, and when you did the geometry, you didn't know that you would even continue high school, so you no longer remember. Right? Okay, so this basically, what happens is, as long as, so consider A being here, that would be the best possible, that would be the extreme case. There, the distance from B to A plus A to C is exactly equal to distance from B to C. If A moves from anywhere on that line, it's going to be greater. There will never be a case where distance AB plus distance AC is less than distance BC. If that is the case, these are not triangles in our world. Right? Okay, let's see. Do you think triangle law of inequality is violated by this heuristic?
No.
I mean, fine. There's a heuristic to be used in answering this question. If it's not going to be violated, why would I spend this much time talking about triangle law of inequality late in the evening? Right? It must have been. Okay, so it clearly is, but the real question is, can you see it? See this guy here. These are the names, right? Remember A, B, C, D, G. So I am considering B, C, G. B, C, and G. B, C, and G. Those are 3 points. Okay, I can compute, so that's a triangle. BCG is a triangle. Now, so I can basically consider the F values of paths to the goal going through those nodes. Okay, so what you will wind up having is this is 8.9, this is 0.2, this is 0.1. This is the cost of B and C. Cost of going from B and C is 0.1. Cost of going from C to G actually is just, in fact it should not be called F, it's H, okay? Cost of going from C to G, C to G, what? 25.1, and okay, I don't know why this is wrong actually. So, and then F of B is cost of going from B to G. Okay, so C to G is, no, according to what I'm showing, okay, I'm sorry, let's look at it. Don't look at the actual graph, look at my heuristics. Okay, according to my heuristic, cost of going from C to G is what? 0. And so the cost of going from A all the way to G is 0.2, according to my heuristic. And similarly, according to my heuristic, cost of going from B to G is 8.8, and the cost to get to B is 0.1, so the total cost is 8.9. And the cost to go from B to C is just 0.1, because that's what is the true graph. That doesn't make sense. That doesn't satisfy triangle of inequality. Another way you could have realized this is, up until here, you thought, when you said this is 8.8, you are saying all paths going through B are going to be at least 8.8 units costly to go to the goal. When you expand B, that estimate can only increase. It can't reduce. If it reduced, then your heuristic is not consistent.
Or you're at the end.
Okay? And if it's, so basically, because heuristics are not true distances, they might wind up, because you're just making these numbers up out of thin air, sometimes they might wind up violating the triangle rule of inequality. You can still use them and you are guaranteed to get optimality, but it will be less efficient. And furthermore, this picture that I showed you about each of the frontiers being bigger than the previous frontier would no longer hold. Okay, but you will reach the goal state optimally. So to make it efficient, there is this idea called path-max heuristic. What path-max heuristic says is, when you compute the f value of a node, check if it is less than the f value of its parent. If so, it doesn't make any sense. So you can no longer, you can't be less than the f value of your parent, because f value of the parent is essentially saying all the paths that go through the parent to the goal. And the paths that go through you to the goal are the ones, just a subset of those paths. That can't be smaller in distance. So path-max heuristic